The esters of glycerol, propan 1,2,3 triol, which can be referred to as fats or oils, can be used to make soaps. This is done by reacting the ester functional groups with hydroxide ions to form glycerol and the carboxylate ions. The diagram below shows the structural formula of a particular fat that gets used to make soap. A student dissolved 8 grams of sodium hydroxide in 50 mils of water and then added 10 grams of the fat shown above. After the reaction mixture was heated, the soap product was extracted and found to weigh 6.45 grams. What is the percentage yield of the reaction? This is asking you to make soap. Brownie points if you know what the name of this reaction is. I think I might have name dropped it for you before. Yeah. You're not required to know this. That's why it's a brownie points question. Yeah. All you've done in the Module 7 course is how soaps work. You never actually did the reaction uh, to make them. Yeah, the reaction is called saponification. Okay, now hear me out. I know you're like, why are we doing this question then if I didn't learn the reaction? The reaction's given to you. Okay, the question's given you a bunch of different masses, and they've given you the first paragraph is giving you enough information to write the equation. Guys, this is just a mole calculation question in the context of a Module 7 reaction. Okay? So we would have a problem with this question if they didn't give you enough information to write the equation, in which case it's assumed that you know the reaction, which they can't test you on because you weren't taught the reaction. Okay, so this is just a mole calculation question. It's just in the context of your soap reaction. Okay, so we need, before we even deal with the calculation, we need to set up the equation and see what's going on. Okay, we're going to comprehend the first paragraph together. All right. So they are making soap. The first sentence tells you that the esters of glycerol, which are the fats or the oils, and this is one of the fats that they use to make soap. Okay, the esters of glycerol, the fats or the oils, can be used to make soap. All right, so that's a context question. Sentence number 2 is actually the one that tells you how to do it. Yeah, this is done by reacting the ester functional group with hydroxide ions to remake the glycerol. So guys, be careful for me. Read the first sentence again. The esters of glycerol get used to make soap. Okay, not glycerol itself. Yeah, the esters of glycerol get used to make soap. And then what do they say in sentence 2? They react the ester functional group with hydroxide ions to form glycerol. Okay, so it's not the glycerol that's reacting, it's the ester of the glycerol, which is the fat. And then when they react it, it forms glycerol and the carboxylate ion. Okay. And then this is a particular fat that gets used to make soap. So the fat is the one that's reacting to make the soap. So this here stays on the left-hand side of your equation. Okay. And then they say, oh, the ester functional group, which is this part here. Right? You know what an ester functional group looks like with hydroxide ions. So generally speaking, it's with hydroxide ions. I'm just going to pay attention to the question as I'm going. It is with hydroxide ions, but the particular form that they use is sodium hydroxide. Okay, so when I write the equation, I could just do OH minus, but I want to keep the question in mind so that I can, makes my life easier when I go to bring in the numbers, yeah? Plus NaOH. Okay, your next job is to figure out how the bonds actually break apart to make your products. Okay. Um, you have two different options for doing that. Yeah. I could figure out the product and then reverse my thinking as I go. Okay. Either, guys, either I learn about how these two chemicals interact with each other and then I'll make the product, or I can make the product first, compare it to this, and see how this broke apart to make the product that I already know. Okay. So I can either move this around to figure out what the product is, or if I already know the product, I can compare the product to this drawing that's right here and then see how it actually changed. Okay, I know what one of the products is. They told me it's glycerol. All right, to form glycerol and the carboxylate ion. And guys, Glycerol is a common name, so we can't draw it, but they gave you the IUPAC name in brackets. Okay? So guys, this looks different, but it's not anything you haven't done. Okay, you know how to draw propan 1, 2, 3 trial. So walk me through it, guys. Propan 1, 2, 3 trial. How many carbons? Okay, 3. Ol, the suffix ol. What functional group is that? Yes, it's a hydroxyl functional group from an alcohol. Can you give me the actual formula so I know what to draw? OH. How many OHs are there? 3 because it says triol. Now look at the numbering. Propan 1, 2, 3 triol. Where do you want me to put the OHs? All on the same carbon or what? Good, one on each carbon. Okay, propan 1, 2, 3 triol is glycerol. OH, OH, OH. Yeah, and then guys, what do I fill the rest of the carbons with to fill up the bonds? H's. Good. Okay, so I don't know how the reaction happens. I never studied saponification reactions, but they give you enough information to figure it out. Yeah, this is the glycerol. Okay, now once you're done getting this down, I'm gonna compare this to the fat structure that they gave me and see how it broke apart. Yeah, because I also need to make the carboxylate ion as well. So if I can figure out how this came about, I can figure out where the molecule broke apart and I'll know what the other half of the product is. Yeah. So guys, I need you to have a look. Yeah, this is the fat. Okay, this is the thing we're trying to figure out how it breaks up. This is what it turns into. Okay, I need to figure out where along this molecule do I break up the bond so then I can, react it and turn it into the products. Yeah. Keep in mind that what came in is an OH. Okay, what came in is an OH and the OH came from here. Yeah, I'm going to draw lines at different points. You're going to tell me where the molecule broke apart. You're going to compare this. Yeah. Option number 1 in red. Option number 2 in green. Option number 3 in blue. Which colored line correctly shows where the fat structure breaks apart to allow the OH to come in? Mm, mm, yeah,
Red.
red. Good. Okay, because guys, imagine this. Keep in mind the OH comes in from somewhere else. Okay, so I know some of you might have been confused. You might have thought it was the green, so then you bring in a H. Yeah, but you don't bring in a H, you bring in an OH. All right. So if the OH, look at this. If the OH comes from one section, then this other half, this is what's left over from the fat. Yeah. And then the part that's there is the red part. Okay. So I'm going to cut it off at the red part. What that means is this is one section that went to make your glycerol, and then this is the other section that went to make what did they say the other product was? Glycerol with the carboxylate ion. Yeah, so this other section is the other product, which is the carboxylate ion. Okay, now guys, just have a look at this. So can you have a look at this for me? This section here, the right-hand side of the fat that we broke it up into, is it one piece? Have a look at it. No, it's not. How many separate pieces is it? I know I've put it in one box, but it's not connected. Where is it? Not two, not two. Try again. 3, yeah? Can you guys have a look here? Look at this. It's not bonded, yeah? These are 3 separate carbon chains, okay? So when you get it out, you're going to get 3, for each fat molecule, you're going to get 3 carboxylate ion thingies. That's what they called it, yeah? Okay, good. So that's going to be my other product. Plus, so I'm just going to copy it out. What is it? It's an O, C double bond O, and then CH2 14, CH3. right, now guys, from year 11, module 2, law of conservation of mass. You cannot lose or create any mass. You have to conserve everything. What's the only element that that I'm missing from the right-hand side? Mm. It's the Na. Okay, so guys, the OH went in to bond with the carbon chain of three. I haven't put the Na yet. Okay, so sort of think of it sort of like switching ionic compounds. So the OH went with the first part of the fat, the second part with which is your carboxylate ion, it's gonna mix with the Na. Yeah, the Na has to go somewhere. Okay, so guys, they kind of swap. Yeah. The OH went with the CH3, the three carbons on the left-hand side. The Na is going to bond with this thingy. Yeah. What's the what's the charge in Na? It's a plus charge. Good. So it's going to be Na plus, which means that the leftover charge on my carboxylate ion is minus. Okay, so guys, I'm not going to do Na line O because your line indicates it's a covalent bond. It's not a covalent bond. Yeah, they told you. What did they say about the carboxylate? They said it's a carboxylate ion. Ion means it has charge. Okay, sodium is also charged. So I'm going to do the charges on each of them and I'm just going to draw them next to each other. I'm not doing Na with a line to O because that implies covalent bond. It's not a covalent bond. Okay. All right, good. You have figured out the saponification equation based on what they give you. If they want to test you on something like this, guys, what I want you to keep in mind is when you go into the exam, they can do this. They just have to give you enough information. Yeah. So I want you, when you go into the exam, trust that you've done enough preparation. You have been doing this all year. Yeah. The chances that you get a question that you genuinely have not studied before is very, very slim. Okay. So if you get a question you feel like you haven't seen before, what that means is they're not testing you on memory, they're testing you on your ability to comprehend the sentences. Yeah. So don't feel like there's something that you genuinely haven't studied. The chance of that is very slim. Okay. Uh, we don't just want an equation, we want a balanced chemical equation. Okay. For each fat molecule, you brought in three OHs, yeah? Because we put in three OHs on here. So then each sodium hydroxide has one OH. If you need three OHs, you need three sodium hydroxides. And then you took out three of these thingies. Remember, we said they weren't connected, so they're three separate sections. So then if you have three of those, then you're going to make three of your carboxylate ions. So I need three of this as well. Okay. So it's a one of the fat, three of the sodium hydroxides, one of the glycerol, and three of your soaps. All right. This is your soap, by the way. Yeah. So you know the structure and action of it. This is your non-polar carbon chain that you're used to, which is, oh, hydrophobic. And then this is your polar head that's hydrophilic. Yeah. This is your soap molecule, guys. Okay. You've got your balanced equation now. I am going to do the calculation question. Okay. A student dissolved 8 grams of sodium hydroxide in 50 mils of water. They added 10 grams of the fat shown above. They reacted the mixture. They heated it up. The soap product was found to weigh 6.45 grams. What's the percentage yield? So when they did the experiment, they actually got 6.45. Percentage yield, we've done questions like this before. You know percentage yield is experimental yield, how much they actually got, which is 6.45, over the theoretical yield, which is how much were they supposed to get based on your calculations, and then you times it by 100. Yeah. They want the yield of the soap, which means I have to get to the soap. So I'm going to do mole calculations with my reagents. Okay. But they've given me two reagents though, guys. So what do I have to check? Because I can only pick one of them to relate to my product. If they've given me both reagents, I have to take the moles and check which one is which kind of. Yeah, I need to check which one's the limiting reagent. Good. They've given me mass. I'm gonna do mass on molar mass to get moles because that's the only way I read my equation. I can't do ratio in terms of mass. I do it in terms of moles. 8.0 grams divided by sodium hydroxide, 22.99 for sodium, 16 for oxygen, 1.08 for hydrogen. What do you get for the moles of sodium hydroxide, please?
0.2.
0.2, thank you. 0.2 mole. And then, guys, they gave you the mass of the fat, okay? So, I think you had fun with this last week. You're gonna do it again, all right? Because I... All right, let's not delay it. I want to do the molar mass calculation separately because it's too big and I don't want to do it in the same mole calculation line, so we'll do it separately. Um, I need you guys to compare each other's answers, yeah? Because I don't have the number for this. How many carbons?
I got 51.
51. Okay, me too. All right, good. 51. How many hydrogens? 99.
I got 98.
98. I need a tiebreaker. 98, okay. H98. How many oxygens? You can use your fingers for this one, see? 6. Yeah. Okay. Can you imagine? Can you imagine doing the entire question right and getting a carry-on error because you counted it wrong? Oh my God, that would suck. Okay, C51H98O6. 51 times 12.01 for carbon plus 98 times 1.08 for hydrogen. Oh, I should also give you a heads up. Don't memorize this, yeah? Because your soaps change. So you know how you have like soft soap and then hard soap and like bar soap and so it was like, oh, lavender and bloody honey, that's a different carbon chain. I'm not joking, okay? Don't memorize this. It's not gonna work. All right? This carbon chain will change. Okay, so you have to figure it out as you go. Yeah? 98 by 1.08 for hydrogen plus 6 by 16 for your oxygen. What's the molar mass of this particular fat? 807.
807.294.
Thank you. 294 grams per mole. Okay, now we do the mole calculation. Moles of your fat, mass on molar mass. How much did they use? They used 10 grams over the molar mass that you guys just calculated, 807.294 grams per mole. What is the moles of the fat?
0.0124.
Thank you.
Approximately.
0.12. Oh, so is it 3 and then keep on going?
Yep.
0.0123 dot 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 mole. Okay, they've given you the moles of both, or you've calculated the moles of both chemicals. The ratio is not 1 to 1, it's 1 to 3. You're not going to compare the moles directly then. You're going to take the moles, you're going to divide it by the coefficient. Yeah. So for NaOH, the coefficient of that when we balanced the equation was 3. So I'm going to do point 0.2 divided by 3, which will be like 0.06 or something. Yeah. And then for the fat, it's 0.0123. The coefficient of that is an invisible one. So it's just going to be the same number. Okay, so guys, compare the two numbers. What's your limiting reagent? Which chemical am I going to relate to the product? The NaOH or the fat? These are your two numbers. The fat. Okay, cool. So the fat is your limiting reagent. I'm going to relate this to the product. And the product is the soap, which is this one. Okay. So the moles of the soap, the coefficient of the soap is 3. The coefficient of the fat is 1. I'm going from 1 to 3. I multiply by 3 to do that. Yeah? 1 to 3 multiplied by 3. So moles of soap is 3 times your moles of fat, which is 3 times the moles of the fat was 0.0123. And then what is the moles of the soap going to be then?
0.03716 dot dot dot.
3716 dot dot dot. Okay. And then they want percentage yield of the soap. The experimental yield that they gave me was 6.45 grams. I need my theoretical yield to be the same unit, which is also grams. Yeah. So I need to turn it into a mass by multiplying by molar mass. So mass of the soap is moles times molar mass. 0.03716 mole multiplied by molar mass of the soap based on this formula. Guys, there's a single sodium. How many carbons? This one's not so bad. Really? Hold on. Mm. Wait. Type it. I'm not understanding. 16. I got
30. Wait, 16.
16. Yeah? The coefficient of the carbon in here is 1. So it's not the hydrogen. I think you might have done the hydrogen. 16, C, 16. And then what's the hydrogen? 48? 48? Oh, no, it's not 48. One more time.
31.
31. Okay. And oxygens. This one I'll be able to read. Thank you. 2. Okay, 1 sodium, 16 hydrogens, sorry, 16 carbons, 31 hydrogens, 2 oxygens. So 22.99 for your sodium. What do you guys say? 16 by 12.01 for your high carbons, 31 by 1.08 for your hydrogens, and then 2 for your oxygens. What do you get for the mass of the soap? I'm going to screenshot the part of the chat where you guys said fat and tell your parents you're bullying me.
Uh, 10.345599.
10.345 grams. This is your theoretical yield. Based on your calculations, this is how much of the soap they was supposed to make if that was how much sodium hydroxide and fat they reacted, yeah? But they did the experiment and then the amount that they actually got was 6.45 grams. When you're doing percentage yield, guys, it is always smaller number over bigger number, okay? Theoretical yield is the maximum amount you can make based on your calculations, yeah? You're never going to make more than that unless something went wrong in your experiment, okay? So maximum So the theoretical yield will usually be the bigger number, and the experimental yield will usually be the smaller number. So 6.45 over your 10.345 times 100 to turn into a percentage. And then what is the percentage yield?
62.35
Thank
approximately.
you. 62.35. And then we will round off to have a look yourself. How many sig figs should we round off to? Oh God. Two, yes. So round off to 62% to two sig figs. Okay. So key takeaway from this particular question, keep yourself calm in the exam if they start asking you questions about reactions that you're not used to doing questions for. It's okay. They have to have given you enough information in the question. Yeah, so trust your ability to comprehend. It's not really going to rely on your study at this point because it's not something to memorize. Yeah. And then in terms of figuring out products, if you can't figure out how the reactants interact, that's okay. Figure out one of the products first and then cancel out the reactants as you go. Yeah. That's the other way of figuring out your reaction. All right.